The second group of equations in the Maxwell equations are the divergence of the magnetic induction B equal to 0. The divergence of B is equal to 0. And that the rotational of the electric field E is equal to minus the time derivative of the magnetic induction. These two equations do not contain the sources of the field, and they constitute relations among the components of the field. So we can count how many functions are in principle necessary to describe the electromagnetic field. Assume that we are in vacuum. So there are no charges around, and the relation between the electric displacement D and the electric field E is simply that they are proportional to each other, okay? And the constant is the permittivity. Similarly, the relation between the magnetic field H and the magnetic induction B is also proportionality, and the constant is the magnetic permeability of vacuum. Okay, so as long as we consider the electromagnetic field in vacuum, or even if particles are present, but the medium is vacuum, B is proportional to H, and D is proportional to E. That means that it is sufficient to know two vectors. One electric vector, like for instance E, and one of the magnetic vectors, for instance B. So knowing these two vectors provides a complete description of the electromagnetic field. It follows that knowing two vectors is equivalent to knowing 6 scalar functions. So in principle, 6 scalar functions suffice to describe the electromagnetic field. And of course, each of these scalar functions depends on position and time in general. Okay. However, when we consider the fact that the second group of Maxwell equations provide relations among the components of the electromagnetic field, we may think that actually fewer components than 6 or fewer scalar functions than 6 are sufficient. And this is true. And to show this, we introduce the potentials. The magnetic potential or vector potential A and the electric potential or scalar potential phi. Okay. How do we introduce them? Well, from the first equation of the second group, divergence of B is equal to 0, it follows, as you remember from calculus, that B can in turn be expressed as the rotational of another vector that we call A, and A is the vector potential, okay? This relation is correct if the space that we are considering is simply connected, and this is of course true in our case. That expression means that if you know A, then you know B, because you take the rotational of A and you deduce B. At this point, one can express B in the second equation of the second group as a function of A. So if you look at the next line, you see that the second equation of the second group becomes rotational of E plus derivative with respect to time of the rotational of A. If you collect the rotational operator, you find that the rotational of E plus the time derivative of A is 0. So you have a vector that is the vector within parentheses whose rotational is 0. And you also remember from calculus that if a vector has 0 rotational, then this vector can be expressed as a gradient of a scalar function that we conventionally call minus phi. And phi is the scalar potential or electric potential. Then you rearrange the expression and find that the electric field is equal to minus the gradient of phi minus the time derivative of A. In conclusion, we have two equations, one expressing B as the rotational of A, and the other one expressing E as minus gradient of phi minus time derivative of A, in which the two fields B and E, that is a total of 6 scalar functions, are actually expressed in terms of 4 scalar functions, because in order to define A, that is a vector, you need 3 scalar functions, and then you have phi, that is another scalar function. So you see the relation among the components of the electromagnetic field at the end reduce from 6 to 4 the number of scalar functions that are necessary. So this is so convenient to use the potentials instead of the field, okay? Another property that comes directly from the Maxwell equations is this. If you take the first group and then you consider the second equation of the second group, you can take the divergence of both sides if you look at the first line. So you have the divergence of the rotational of H, and this from calculus is an operator that provides identically 0. Okay, so the divergence of the rotational of any vector is 0. And at the second, on the right-hand side, you have the divergence of J plus the derivative with respect to T of the divergence of D, but this divergence is equal to the charge density rho because of the first Maxwell equation. So when you combine these calculations, you find the very well-known continuity equation of the electromagnetic theory that tells you that the time derivative of the charge density plus the divergence of the current density is equal to 0, okay? Essentially, an equation like this expresses the conservation of charge. You remember from calculus, if you take any volume and then you integrate this equation over the volume, you find that the variation of the total charge inside the volume is equal to the flux of J across the boundary of the volume. So this is the meaning of the continuity equation, okay? Now we must specify these expressions that are fully general to the case of a semiconductor. So essentially we must specify the form of the charge density rho and of the charge of the current density J. So as for the charge density, you remember the charge density in a semiconductor is equal to the elementary charge Q times the concentration of holes that are positive minus the concentration of the electrons, the minus because electrons are negative, so they contribute negatively to the charge density, plus the net ionized dopant concentration, capital N, that is Nd plus minus Na minus. In the first of the Maxwell equation, we have the displacement, the electric displacement vector D. The question is, what is the relation between the electric displacement and the electric field? We expect that the ratio of the two should be the dielectric constant, okay? However, it is not the dielectric constant of vacuum, and this is for the following reason, that if you look at the expression of the charge density, you see that we are using the concentrations. So we are using P, N and capital N, not the sum of the individual charges of the holes, electrons, and ionized dopants. Okay. When you consider the concentrations, you already imply that you have performed an average over some small volume of the semiconductor. And the same when you use the current density, you are not using anymore the individual velocity of each particle. You are using the average velocity of the electrons and holes. When you perform these averages, okay, you consider volumes in which there are many particles inside. So it is not correct anymore to use for the relation between D and E, the permittivity of vacuum. We must use the permittivity of the semiconductor. This is why in the first relation, D is proportional to the electric field according to epsilon SC. Epsilon SC is the permittivity of the semiconductor. When you consider the complete ionization condition, Nd plus, as you remember, becomes Nd. All donors are ionized. Na minus becomes Na. And it follows that the net dopant concentration is prescribed. It's a function that we know because we fabricate the profile of the dopants technologically, and we know it at each position in the semiconductor. There is no dependence on the Fermi level anymore in the net dopant concentration. When you consider the current density, you remember we already defined the current density Jp of the holes, that is equal to the elementary charge times the concentration P of the holes times the average velocity Vp of the holes, and the current density of the electrons, that is minus Q times the concentration N of the electrons times the average velocity of the electrons. Okay. Let's now consider the equilibrium condition. Okay. In the equilibrium condition, obviously, there is no dependence on time. So the time derivatives, when they appear in the equations, are equal to 0. Okay? Of course, in equilibrium, there are no currents. Okay? So individually, Jn and Jp are 0. And also the general relation that expresses the electric field, that is electric field equal to minus gradient of phi minus dA dt, reduces to E equal to minus gradient of phi because the time derivative is 0, okay? So in equilibrium, we have a sort of strong simplification of the relations. If, in addition, we are in the non-degenerate situation, which we always will assume from now on, okay? You remember that if the semiconductor is non-degenerate, then the concentration of the electrons and the concentration of the holes are defined in terms of the electric potential through exponential relations, okay? For instance, among those that we have considered in the last lessons, it is convenient to use n equal to n up 0 exponential of q phi over kt. And similarly, p is equal to p up 0 exponential of minus q phi over kt. Okay, so n and p only in the equilibrium condition, are functions of the electric potential. So the form of this function is given. Okay. If you then go back to the expression of the charge density, the first line of the page, you see that capital N is a prescribed function of position. P and N are known function of phi. So you may conclude that in the equilibrium situation, the global charge density of the semiconductor is a function that depends on phi and position. Okay. There is an explicit dependence on position because the doping depends on position. Now, since we have that the time derivatives are 0 and the current densities are 0 and the electric field is just minus the gradient of phi, you don't need anymore the full set of the Maxwell equations. You actually need only one equation, the first one. Divergence of D equal to rho, because you can write when you take the divergence of D equal to rho, rho is some function that depends on phi and r. D is, as you remember, the permittivity of the semiconductor times the electric field. The permittivity is a constant, so you can take it out of the divergence. And E is minus the gradient of phi. So when you replace this into the expression of this divergence, you find the last line of the page in which the left-hand side is minus the permittivity times the Laplacian of the electric potential. And the right-hand side is simply the expression of the charge density in which the concentration of holes and electrons have been expressed explicitly as a function of the potential. So you see, we have reduced the full set of Maxwell equations in the special case of equilibrium to a single equation. Of course, this is the Poisson equation, in which the right-hand side depends non-linearly on the unknown. The unknown function of this equation is, of course, the electric potential phi, because capital N of R is given, is known, okay? So in order to solve this equation, we need boundary conditions, okay? And we shall examine the boundary conditions soon. So for the moment, we assume that we do have the boundary conditions. We solve the equation, and we find the value of the electric potential everywhere inside the semiconductor or at the boundary of the semiconductor. At this point, you remember that minus Q phi is the electrostatic energy of the electrons, that the electrostatic energy of the electrons plus the function that we call EF bar is equal to a constant. So we have all the ingredients to calculate all the remaining properties of the semiconductor. In this easy case, once you have calculated the solution of the Poisson equation, and because of this you know phi everywhere in the semiconductor, you can simply place phi in these exponents, and you immediately calculate the concentrations N and P at any position of the semiconductor. This is easy because the semiconductor is non-degenerate, so you don't have to calculate the Fermi integrals, okay? You just use the exponentials. So the equilibrium case reduces to the Poisson equation, okay? If you are in the non-equilibrium case, you cannot use the relation between electric potential and concentration of electrons or electric potential and concentration of holes anymore, okay? You don't have anymore the Fermi level when you are in the non-equilibrium situation. You don't have the Fermi statistics. You cannot express anymore the concentrations N and P as Fermi integrals. These two relations here do not exist anymore when you are in the non-equilibrium condition. So you must consider that N and P are unknowns themselves, and also the average velocities also are unknowns themselves. So you remember the definitions, okay? When you take the integrals over the K space, small n is the integral over the conduction band of Q phi. Phi is the general or generic occupation probability. P is the integral over the valence band of Q times 1 minus phi, and the average velocities are given by the expression that you already met a few lessons ago, okay? What happens in this case? In this case, the first issue is try to separate as much as possible the expressions related to the conduction band from the expressions related to the valence band. Okay, and for this we may start from the general form of the continuity equation. So unfortunately, I cannot write, okay, but I can simply state what happens. Take the general form of the continuity equation that is visible in the last line of the page. And then you remember the charge density rho is equal to Q parenthesis small p minus small n plus capital N parenthesis. On the other hand, if you consider that we are, by hypothesis, in the complete ionization condition, the concentration of the dopants is a function of R, of position, but in no way is a function of time. So the time derivative of the concentration of the net dopant is 0. So essentially you have time derivative of QP minus time derivative of Qn. So the time derivative becomes two terms. One term contains only the time derivative of P, and the other term contains only the time derivative of N. Next, you go to the divergence of J. You remember J, the current density, is equal to the sum of two contributions. One is the contribution of Jp from the holes, and the other is the contribution from Jn, that's the electrons, okay? So also in this case, it is possible to separate the divergence of J as the divergence of Jp plus the divergence of Jn. At this point, you bring all terms containing N to the right. So this general expression of the continuity equation becomes an equality that reads, on the left-hand side, you have time derivative of Qp plus the divergence of Jp. So on the left, you have only quantities that depend on the holes. On the right-hand side, you have time derivative of Qn minus divergence of Jn. So you have on the right-hand side a quantity, an expression that depends only on the electrons, okay? So you can say that these two, it's like two partial continuity equations, one related to the holes on the left and the other one related to the electrons on the right, okay? And they are equal at each point of space and at each instant of time. Can you state that each side of the equation is equal to 0? Of course not, okay? You may only state that these two terms are equal to each other, okay? So in order to proceed, we use some sense of humor and adopt a very old trick of the mathematicians that you probably know very well. When mathematicians do not know how to deal with the quantity that they find in the equations, Well, they give it a name, okay? So we give some name to the left-hand side and some name to the right-hand side of this equation, okay? So after all this elaborate analysis, what we do is that we split the continuity equation into two continuity equations that you see in the last line here of the page. I described the procedure using Jn and Jp, but you remember that if you take Jn and you divide by the charge of the electron with the minus, you obtain the flux NVN, and the same for the holes, okay? So the two continuity equations that you find in the last line are simply the result of splitting the original continuity equation of the Maxwell equations into two parts. One part is related to the electrons only, and it is the one on the left, and the other is related to the holes only, okay? The right-hand sides are non-zero. They are given some name, as mathematicians do, okay? We call them Wn and Wp. From the analysis, they should be equal, and actually eventually we shall see they are equal, okay? So Wn is Wp. For the moment, we keep two different symbols just to remember that, where they belong, okay? The important thing is that Wn and Wp are non-zero, okay? What is the meaning of Wn and Wp? The meaning of them can be understood remembering the meaning of the continuity equation. So for instance, take the first equation and integrate this equation over some volume, okay, of the physical space. So the integration of dN over dt over the volume provides the variation in time of the total number of electrons in the volume. The integral of the divergence over the same volume, as you remember from calculus, is the total flux of the particles across the boundary of the volume, okay? So if Wn at the right-hand side were zero, which is not, but assume that it is zero, the continuity equation would tell you that the variation in time of the number of electrons in the volume equals the flux, with the minus sign, the flux of the electrons crossing the boundary, okay? The existence of a function Wn that is non-zero in the equation, and this function also must be integrated over the same volume, tells you that there is another reason for the change of the population of electrons in the volume, okay? So this looks odd, okay, because I'm sure that you are very well accustomed to being told by the teachers that nothing can be created and nothing can be destroyed. Whereas it looks like Wn and Wp could be associated to the destruction or creation of electrons or holes, okay? So this looks odd, but I can give you an easy example. okay, of how this can happen, okay? Assume that instead of talking about particles, we talk about students. And we are considering the students that are in a classroom, okay? And then we want to measure the variation in time of the students that are in the classroom. And this is very easy because you stay at the door of the classroom, and if there is a student that enters the room, then you count it as a positive contribution. So it is a positive contribution of the flux that determines an increase in the population inside the classroom. Whereas if there is a student that exits across the door, you count it, or her or him, as negative. Okay, so it's a negative contribution to the population. Okay, of course, there is no other possibility in this example for the number of students in the room to change. They change because some student leaves the room, and in this case they decrease, or they increase if some other student enters the room. Okay? Now let's take a slightly different example by adding an extra property. Okay? We want to count the variation in time of the number of students that are in the classroom and are not sleeping. Okay? So you can still stay at the door and count the students that enter and the students that exit the room, okay? But if one student that is sitting in the room falls asleep, this student will contribute with 1 to the students that are sleeping. So it will a negative contribution to the students that are non-sleeping, okay? So if we count an extra property, not only that the students must be inside, but they should not sleep, okay? Then we have an additional term, and this term must be expressed as the function W, because they are not crossing the boundary of the classroom. They sleep, they fall asleep, or maybe they wake up where they stand, okay? So in this case, we need an additional function that belongs to the volume and must be integrated over the volume as well, okay? So in the case of the semiconductor, what is the extra property that we should consider in this analysis? The extra property is that when we consider the electrons of the conduction band, we imply that these electrons have an energy that belongs to the conduction band. So if an electron without moving in space makes a transition that brings the electron into the valence band, this electron is lost for the conduction band. So we should count it as a negative contribution. If another electron comes from the valence band into the conduction band without moving, okay, so staying within the volume that we are considering, but changing its energy, then we also should count it as a positive contribution to function Wn. And the same analysis applies to the holes in reverse, okay? So eventually the meaning of n is written in the page, and Wn is the difference between the number of electrons entering the conduction band and those leaving the conduction band per unit volume and time, because if you look at the units of the different terms, you find that Wn and Wp are numbers divided by volume divided by time. So Wn is called the net generation rate of the conduction band. Similarly, Wp is the net generation rate of the valence band. That is, it is the number per unit volume and time of holes entering the valence band less the number per unit volume and time of holes leaving the valence band. Okay, so splitting the global continuity equation that comes from the Maxwell equations into two for two separate populations of particles imply the need of introducing the net generation rates. Of course, when we are in the equilibrium condition, there is no dependence on time, so the n over dt is 0 and dp over dt is 0. The average velocity also are 0, so there is no flux of particles, so automatically Wn and Wp are 0 at equilibrium. This is also called as detailed balance condition. Okay, Wn and Wp are individually equal to 0 at equilibrium. So at this point, we must consider these two continuity equations as two additional equations that must be used when we are in the non-equilibrium condition. Okay, the question is, are they sufficient? And the answer is no. Why? Because we have introduced two equations, the two continuity equations for the electrons and holes. But we have four new unknowns that are n and p, the two concentrations, and the two current densities or the two fluxes, or the two average velocities, as you like. Okay, so these equations are, of course, welcome, but they are not sufficient, because it's two more equations, four unknowns. Okay, of course, we assume that the net generation rates Wn and Wp in themselves are not unknown. So we assume that we are able to express Wn and Wp using the existing unknowns. Okay, so Wn and Wp should not introduce more unknowns. Okay, otherwise we would be lost. But they don't. Okay, so they can be expressed in terms of the existing unknowns. Okay. One more comment, but we shall elaborate more in the next hour. The non-equilibrium case can be split into two subcases. One subcase is the so-called steady state condition. So if you consider a semiconductor device in a non-equilibrium condition, but such that the applied voltages are constant with respect to time, so nothing in the problem depends on time. So we are in a non-equilibrium condition, but it is time independent, and we call it steady state. So it's a little bit simpler, okay? If instead the boundary conditions of the problem depend on time, then we do have the time derivatives in the problem, and we have a fully time-dependent non-equilibrium condition. Okay, so we have to split the two subcases, and as we shall see, the steady-state condition is somewhat simpler than the time-dependent condition. For the moment, we stop. If there are questions, we still have 2 minutes before the intermission. And if there are no questions, okay, we shall meet each other in 10 minutes from now. Thank you. Okay. You remember that we were commenting the two possible cases of non-equilibrium. One is steady state, and the other one is a fully dynamic condition, okay? So let's examine first the situation in steady state. In steady state, we can still express the electric field as minus the gradient of phi, because the time derivative of the magnetic potential is zero, because we are in steady state. If the electric field depends only on the electric potential, we substantially split the set of Maxwell equations into two parts and keep using only the Poisson equation. So in the steady state non-equilibrium condition, out of the Maxwell equations, we use only the Poisson equation. What is the difference between this case and the case of equilibrium? The difference is that in equilibrium, the concentrations of electrons and holes are functions of the electric potential, as you remember, okay? I go back by a few pages, okay? You remember in equilibrium, you have the equation on the last line of the page. So just one equation with only one unknown, that is the electric potential. In the non-equilibrium condition, also the concentrations are unknown, but if you are in steady state, you have the Poisson equation, and the Poisson equation should be written, as you can see in the first line of this parenthesis, that is minus permittivity times the Laplacian of the electric potential is equal to the charge density, and the charge density is Q times P minus N plus the net dopant concentration, okay? In which P and small n are also unknown, so we must couple this equation with the two continuity equations that we examined earlier, and possibly with other equations that complete the model, and that we shall see in a minute. The second equation on the second line is again the Poisson equation, because when you have a device, and you know very well that there are important devices like the MOS devices, like the MOS transistors, for instance, in which an essential part of the volume of the device is made of insulator, okay? So in the insulator, there are no mobile charges. There are no mobile electrons or mobile holes, okay? In principle, in the insulator, there should be absolutely no charge, okay? But it may happen that in the insulator there is some fixed charge for some reason, okay? So the second equation is the form that the Poisson equation takes when you consider the portion of the volume of the semiconductor device made of an insulator. A typical insulator is the gate oxide in the MOS transistor. So if you have a material that is the, for instance, silicon oxide, then the permittivity is different from the permittivity of silicon alone. So this is why in the second line you have the permittivity with the symbol epsilon ox, because it is implied that it is the oxide of silicon, okay? And on the right-hand side, there are no free charges, so there are no holes or electrons. There could be some fixed charge that we call capital N ox. Okay, we hope that there is no such a charge, but in some situations it could be present. So in this case, this is the form that we have for the Poisson equation in the non-equilibrium steady state situation. When then we go to the more general case, that is non-equilibrium dynamic condition, then we must express in principle the electric field as minus the gradient of phi minus the time derivative of the vector potential. This is very, very inconvenient from the practical standpoint, because when we have the magnetic potential, then we must couple together all the Maxwell equations. We cannot avoid using the full set of the Maxwell equations. So in that case, we must use the semiconductor equations plus the Maxwell equation, okay? This is somewhat inconvenient. It's quite heavy for the calculations. So we may be induced to seek for some approximation that avoids using the time derivative of the magnetic potential. So we now must look for some reasoning able to eliminate the time derivative of the magnetic potential, okay? Obviously, we can say, if we go to the limit of the steady state condition, of course, the derivative of A with respect to time will be zero identically, okay? This is not the case if the quantities involved depend on time, but we may say, if the change with respect to time is slow, then the time derivative of A will be small, enough to be neglected, okay? So we must seek for a condition in which the time variation of A is small, okay? Then the question is, why is the magnetic potential changing with time? You remember, it changes with time if we have that some of the boundary conditions of the problem are changing with time. So for this reason, we are considering here a very simple structure, okay? You see, it is the upper part, the channel part of the MOS transistor. So on the left, the black bar is the source contact. that supposedly is constant with respect to time. On the right, we have the drain contact that changes with time. And this is the gate contact that possibly also changes with time, okay? What is the dependence on time of the voltages that are applied to a semiconductor devices? They may be general signals that depend on time. They may even be pulses. In digital computers, they are pulses, okay? So assume that VD, for instance, has a spectrum, has a complicated dependence on time, okay? Consider now the spectrum of VD and consider the largest frequency of the spectrum. So you consider the monochromatic component of the applied voltage that changes, that is the fastest in changing, okay, because it is the largest frequency of the spectrum, okay? So this is the worst possible case. This largest frequency in the formula that you can see below is called Ni max. It's the maximum frequency of the spectrum of the applied voltages. Its inverse, capital T min, is the minimum period, okay? Now, the question is, what happens when the applied voltage changes with respect to time? Well, obviously, if you take a point immediately underneath the contact, okay, if you change the voltage at the contact, the voltage at this point will instantly change with the same rate, okay, because this point is at the contact, practically is inside the semiconductor very near to the contact, okay? Then take another point anywhere in the device, okay? So that the distance between the point near the contact and this other general or generic point is some distance d, okay? So when you change the voltage at the drain, the electric potential or the electric field at the position underneath the drain contact will change immediately. The electromagnetic field in the other point will change after a time, because the electromagnetic perturbation takes some time to propagate from the drain contact to the interior of the material, okay? So we can easily calculate the time that is necessary for this propagation to occur. So the internal point will understand with some delay that the potential at the drain contact has changed. What is this delay? Let's call it delta T. Of course, delta T is equal to the distance d divided by the propagation velocity of the electromagnetic field at the frequency Ni max. So it is the phase velocity of the electromagnetic field at that frequency. Let's call it UF, okay? So delta T is the time that it takes for the perturbation to propagate from the contact to the interior. T min is the typical time in which the boundary voltage changes, okay? If it happens that delta t is much smaller than capital T min, this means that the propagation is practically instantaneous. That means that the internal point feels the change in the electromagnetic field before any significant change occurs at the contact. Okay, so this is a situation in which we can consider approximately a steady state condition, because the propagation is much, much faster than the change of the voltage at the contact. At this point, we can reverse the equation. We can extract Nmax, that is the maximum frequency of the applied voltages, such that this inequality applies, okay? So the maximum frequency is UF over D. If we were in vacuum, UF would be the speed of light in vacuum, that is 3 times 10 to the 10th centimeters per second, okay? Assume that in the material this velocity is smaller, so drop the 3 and take UF equal to 10 to the 10th centimeters per second, okay? The issue is, what is D? How do we take the length D, okay? We may have different choices. One possible choice is if you consider the full chip, okay, the full integrated circuit, okay, you can take D as the diameter of the chip, like 2 centimeters, okay? But this would be nonsensical, okay? Because the issue is calculating the propagation inside a region in which the important electrical phenomena of the single device occur, not the whole chip that contains not only many devices, but also the connection lines, okay? So taking the diameter of, or the diagonal of the chip is nonsense for D. Another possible choice is taking D equal to the thickness of the silicon wafer. Okay, the thickness is about 0.5 millimeter. Okay, but this is also nonsensical, because in the bulk of the silicon wafer there are no electric phenomena of interest. Okay, all the important electric phenomena happen at the surface. Okay, so if you consider the MOS architecture, the only sensible choice for D is the length of the channel of the MOS transistor. Okay, many years ago, typical length of a channel used to be 1 micron. That is 10 to the minus 4th centimeters. Okay, so if you look at the ratio, you find that the maximum frequency of the applied signals, if you take 1 micron as the typical length of the channel of the MOS transistor, is 10 to the 14th hertz. Okay, 10 to the 14th hertz is enormous, is around the visible range of the electromagnetic radiation, but the signals applied to the contacts of integrated circuits are in the range now of gigahertz. So they are many orders of magnitude smaller than that. So even if you take a channel length of the old style devices equal to 1 micron, we are already in the safe situation. Okay. Modern devices have a channel length of the MOS transistors that is much, much smaller than that. Could be 40 nanometers. Okay. So that limit becomes safer by at least one order of magnitude. Okay. So in conclusion, the smallness of the semiconductor devices is such that the propagation time of the signals inside the device is practically negligible. So it is as if the applied voltage do not change in time. And fortunately for this, we can safely neglect the time derivative of the magnetic potential. Okay, so even in the non-equilibrium dynamic situation, we can neglect the time derivative of the magnetic potential. We assume that E is equal only to minus the gradient of phi. So we have to solve out of the Maxwell equations. It is sufficient to consider only the Poisson equation, and we neglect all the rest of the Maxwell equations. Okay, this approximation, that of course is very welcome because it simplifies very much the model, is called a quasi-static approximation. Quasi-static approximation. Beware that we are neglecting the time derivative of the magnetic potential. We are not allowed to neglect the time derivative of n and the time derivative of p if we are in a dynamic condition. dn over dt and dp over dt must be kept in the equations, okay? The quasi-static approximation does not apply to these two terms because the phenomena that determine the variation in time of n and p are much, much, much slower than the propagation times. Okay, so in dynamic condition, the n over dt and dp over dt must be kept in the equations. Now we are left with the problem that I mentioned before. That is, the two continuity equations, those in the last line of this page, are not sufficient because there are two equations with four unknowns. So we must find extra equations, and for instance, we must be able to find extra equations able to describe the fluxes. The fluxes are small n Vn and small p Vp. Or equivalently, the current densities, okay? Jn, that is proportional to nVn, or the whole current density Jp that is proportional to pVp, okay? Providing an expression for the current density essentially amounts to describing the transport of carriers in the material, amounts to expressing the laws by which particles move, that is, are transported across the semiconductor material. And there are two fundamental mechanisms by which carriers can move inside the semiconductor. One mechanism is really obvious. Since electrons are charged particles and holes also are charged particles, if there is an electric field, this field will force the electrons and the holes to move, okay, because it is a force applied to them. This first contribution to transport is called drift. A second contribution to transport is due to another mechanism that is called diffusion. Diffusion is a transport mechanism by which the particles can move also without the presence of any field. Actually, diffusion occurs also with neutral particles, okay? If you drop some droplets of ink in a glass of water, you see that the ink diffuses everywhere, in every direction, okay? And when in the position where the droplets touch the water is very dark. But if you wait for some time, the color will become paler and paler, and eventually the ink will distribute over the whole volume of water. Okay, so diffusion is a mechanism in which particles move from the regions where the concentration is larger to the regions where the concentration is smaller. Okay, but because of this motion, the concentration tends to equalize and eventually the diffusion stops. Okay, so we now shall examine separately these two mechanisms, drift and diffusion, and then we shall put them together. We start with considering diffusion, okay? When we have a purely diffusive flux, we have that particles move, meaning there is a non-zero flux of the particles because their concentration is non-uniform. So particles tend to move from the regions where the concentration is larger to regions where the concentration is smaller. What is the typical indicator that tells you that the concentration of the particles is non-uniform? The indicator obviously is the gradient. Okay, if you have a non-zero gradient, that means that the variation, the concentration of the particle changes with position. Okay, we assume a very simple model. We assume that the flux not only depends on the gradient of the concentration, but that this dependence is linear. So we assume that a purely diffusive flux is such that the flux is proportional to the gradient of the concentration. For the electrons, you can see it on the first line on the left. We have that the purely diffusive flux of electrons, n times Vn, is equal to the gradient of n, the gradient of the concentration of the electrons, times a constant. This constant is called dn, and it's called the diffusion coefficient of the electrons. The diffusion coefficient is positive definite. Okay, you remember also that the gradient of a function points towards the direction in which the function increases, okay, whereas the flux goes into the direction where the concentration decreases. So we need a minus sign, okay? So globally, the expression of a purely diffusive flux of electrons is NVN equal to minus the diffusion coefficient dN times the gradient of N. And like for the holes, the expression is identical for the holes. We only replace small p to small n. If you check the units, you find that in all cases, the diffusion coefficient has the units of an area divided by a time. Now we go from the flux to the current density. So when we consider the current density of the electrons, Jn, we multiply the flux time by minus q. So the minus sign cancels, and the diffusive component of Jn is plus q dn gradient of n. Similarly, when we want to express the whole current density, we multiply by plus q. So we have minus q dp gradient of p. Okay, so we now for a moment, we put it aside and we consider the other transport mechanism that applies, of course, only to charged particles. That is the purely drift. It is also called ohmic flux. Okay, so when there is a drift or ohmic flux, it means that there is an electric field inside the material, and of course this electric field is a force that is applied to the particles and moves the particles. So it determines a flux of the particles. Okay, in the purely ohmic situation, that means when we have only this phenomenon, the easiest form of the relation between the current density and the electric field is the linear form. So we assume that the current density of the electrons is proportional to the electric field through a constant that we call sigma n. And as you very well remember, this is the electron conductivity. If you have only electrons, Jn equal to sigma n times the field is nothing else than the law of Ohm in local form. Okay, the local form of Ohm's law. Okay. In this case, we have two types of particles, electrons and holes. So you have also the equation for the holes of the drift form, that is Jp drift equal to sigma p, that is the conductivity of the holes, times the electric field. For the moment, we do not have an expression for the conductivity sigma n and sigma p, but we shall have it very soon. Okay. Now, assume that the non-equilibrium situation that we are considering is not too far from equilibrium. Okay. And also assume that the two phenomena, that is the diffusion due to the non-uniformity of the concentrations and the drift due to the presence of the electric field, assume that these two phenomena occur together in the material. Okay? If the problem is not too far from equilibrium, it can be demonstrated that we can simply add the two effects together. So we can use the superposition principle, okay? So in this case, the expression or the global expression of the current density for the electrons is equal to the sum of the two terms, drift term and diffusion term, okay? Similarly, the expression of the current density for the holes is the sum of the two drift and diffusion terms for the holes, okay? You remember that when you are in the equilibrium condition, so when all the external perturbations have been eliminated and the semiconductor goes back to equilibrium, the two current densities are zero, okay? So Jn is zero at equilibrium and Jp also is zero at equilibrium. This does not mean that each diffusion term is individually equal to zero and each drift term is individually equal to zero. Jn, for instance, may be equal to zero also if drift and diffusion terms are non-zero but opposite to each other, equal and opposite to each other, okay? And this is what typically happens if the semiconductor is non-uniform. If you have a non-uniform semiconductor and consider the equilibrium case, non-uniformity will induce diffusion. But non-uniformity of the charge will also induce a net charge density at each position in the semiconductor that gives rise to an electric field. And this electric field will balance diffusion. Okay, we shall see it better as soon as we have determined the expression of the drift terms, okay? So you may have an equilibrium condition that is non-uniform, nothing moves, because the drift and diffusion components of each current density balance exactly each other, okay? Now the issue is to find the expression for the conductivities, okay? Of course, the superposition effect, okay, can be demonstrated. There is a much longer calculation that demonstrates that to some order of approximation, the drift diffusion form of the equation is correct, okay? Actually, this is also the name, as you can see above. These two equations are called the drift diffusion transport equation for electrons and holes, and the mathematical model based on this equation is called the drift diffusion model of semiconductors. Now let's try to extract heuristically from some microscopic consideration the expressions of the conductivities, okay? What we do is the following. We consider, for a moment, a single particle. It could be one electron or one hole, okay? You remember that the inertia of the electron or the holes in a semiconductor is determined by the effective mass, okay? So let's use for the effective mass a general symbol that is m star, as you can see in the first line, okay? If there is an external force like the electric field applied to the particle, by Newton's law, the acceleration A will be related to the external force by this equation. So A times the effective mass is equal to the force. Let's divide by the mass. And remember that the acceleration is the time derivative of the velocity. This velocity u that you see in the middle is the velocity of the individual particle, electron or hole, not an average velocity, okay? So we have du over dt, and then we remember that electrons are negative, so the force produced by the electric field over an electron is minus q times the electric field. If we are considering a hole, the force will be positive, plus q electric field. So with the double sign, we consider at the same time the electron or the hole. So we have time derivative of velocities equal to plus minus q over m star times the electric field. And the electric field may depend on time, of course. In a dynamic situation, it depends on time. Now we integrate this relation over time. And if you consider the central part of the second line, where the integral of the electric field is visible, okay, you see that we use for the integration limits, the second integration limit is some generic time t. The first integration limit is t minus tau. So it is some time before t. Tau is positive, of course. It's some time earlier than t. We don't specify it for the moment, okay? When you integrate the left-hand side, of course, you find u at t minus u at t minus tau, okay? Now, let's assume that tau is very short. So short that the electric field does not change too much along a time equal to tau, okay? So we can consider in the integration that E is a constant, okay? So the integral can be approximated as electric field times tau, okay? So the issue is, what is this tau? To describe what tau is, we must figure out what is the typical trajectory of one electron or one hole in the semiconductor. Consider one electron. You have an electron that travels in space, and it is subjected to the external force, the electric field. So it is accelerated by the electric field. After a while, this electron has a collision with something else, another electron, a nucleus, a photon, whatever, okay? So we can figure out the trajectory or the evolution, the dynamic evolution of the electron inside the crystal as an alternation of what we call free flights, during which the electron is subjected only to the external field, and collisions, okay? So this is enough to specify the times t and t minus tau. T is any time during a free flight. Tau is the time interval between the last collision event and t. So it is the time that has elapsed from the last collision undergone by the electron. Okay, so this is why tau is so short, because the typical time between collisions is smaller than a picosecond. Okay, and the electric field does not change much over a picosecond. At this point, you take the expression u of t minus u of t minus tau, etc., and average this expression over the whole set of electrons of the conduction band. So the parentheses with the tip indicate average, not average in time. It's a statistical average, average over all particles. Okay. So you average u of t, you average u of t minus tau. You don't average q, effective mass, and the field, because they are, of course, the same for all particles, but you average tau. Okay, tau may be different from one particle to another. Now, what is the average of u? Of course, it is v sub n if you are considering electrons. Actually, v sub n of drift, because in this case, the only reason for the motion of the particles is the electric field, okay? Or it is Vp of drift if you consider holes. Similarly, the average of tau is a time that is indicated as tau sub Pn for the electrons, or tau sub Pp for holes. The second index, N or P, stands for electron or hole. The first index stands for momentum. So tau Pn is called the momentum relaxation time of the electrons. Tau Pp is the momentum relaxation time for the holes. And then you specify the symbol of the mass. M star becomes M sub n or M sub p, okay? M sub n and M sub p are still combinations of the entries of the mass tensor, okay? But they are not average masses, they are another thing, okay? Other combinations, okay? What is the fundamental issue? The fundamental issue is that the average, the statistical average of u of tau of t minus tau is negligible if the electric field is small. And the reason is that the collisions are essentially randomizing the motion of the particles. So when a particle completes a collision, its velocity may be oriented anywhere in space. So when you take a statistical average of a vector that can be oriented anywhere, okay, all the positive components will cancel the negative components, and the average will practically be equal to 0. Eventually, what you obtain is that Vn or Vp is proportional to the electric field, and the proportionality, using the symbols that we have introduced above, are that for the electrons you have a minus sign, so the average velocity is proportional to the electric field with a minus, and the constant is q tau Pn over Mn, This constant is called mobility of the electrons, and is indicated with mu n. Similarly, for the holes, we have Vp proportional to plus a constant times the electric field. And this constant is Q tau pp over mp, that is the mobility of the holes mu p. Okay. At this point, you may simply remember that if you have the average velocity Vn, Vp, you obtain the current density. So for the electrons, you take Vn and multiply by minus Qn. Then you replace Vn as minus mu n times E. You obtain that Jn is equal to Q mu n times the field. And this immediately shows that the expression for the conductivity sigma n of the electrons is charge Q times mu n times n. We anticipated that when we discussed the effect of temperature of conductivity. This is the point. Q is universal constant. The mobility degrades a little when you increase temperature, but n increases exponentially in a semiconductor when you increase temperature. The same applies for the holes. So the conductivity of the holes, sigma p, is Q mu p times p, same thing, okay? So we have eventually found out the expression of the conductivity, okay? Again, this is a heuristic argument, okay? But with the longer calculation, you can indeed show that these are the correct expressions of the mobility for the electrons and holes. The units are an area divided by a voltage divided by a time. So square centimeters over volt over second for the mobilities. We stop here. If there are questions, you can activate the microphone. Otherwise, we shall continue tomorrow afternoon. Thank you.